Welcome to Unit 2, Lesson 1, Projecting and Scaling. Unit 2 is entitled Dilations, Similarity, and Introducing Slope. So we're going to see that a dilation is when we can take a shape, making it larger or smaller proportionally. And we'll do that by taking a point along the line to another point whose distance is a certain distance away. Scale factor comes into play because that's the number used as the multiplier in scaling. That'll tell us how many times greater or how many times smaller the figure is. So in the last unit, Unit 1, we were talking about congruent figures, and we saw that this was shown when there's a rigid transformation that moves the first figure so that it fits exactly over the second. But for similarity, when things are similar, this is shown when there's a sequence of rigid transformations and dilations making the shape bigger or smaller so that it can fit, we can move it and have it fit directly over the second. So when dilations are involved, when we're making the figures bigger or smaller proportionally, we'll see that those shapes can only be similar. Transformations, as we've been talking about, can be a translation, a rotation, a reflection, a dilation, or a combination of these. So you may need to hit pause on the video so that you can get all of these vocabulary definitions down. You'll definitely be seeing them on an upcoming quiz. Looking at our first question, rectangle A measures 12 centimeters by 3 centimeters, while rectangle B is a scaled copy of rectangle A. Because it's a scaled copy, we know it's either larger or smaller proportionally. So it asks us to select all of the measurement pairs that could be the dimensions of rectangle B. So I went ahead and I drew what the problem said. It told us that we're starting with rectangle that is 12 by 3. Rectangle A is 12 by 3. The question is, could any of these rectangles be a scaled copy? So what we need to do is we need to find what is the scale, if there's scaled copies of the other copies. So let's take a look at A. A said 6 centimeters by 1.5 centimeters. It said 6 centimeters by 1.5. I want us to note that we're looking at the biggest compared to the smallest, the biggest side of 12 compared to the smallest side of 3. So the biggest side in this next possible rectangle, 6 centimeters by 1.5 centimeters, I have to put it as a ratio, which is just a fancy word for a fraction, where we're looking at the biggest compared to the smallest side. So we're asking ourselves, is 6 over 1.5, is that equal to 12 over 3? I had to put the biggest number on the top and the smallest number on the bottom. So you may be asking yourself, how do I get from 6 to 12? Well, that's times 2. How do we get from 1.5 to 3? Well, that's times 2. So we can see that 12 thirds is twice the size of 6/15. So these must be scaled copies. If we look at question A, we can definitely circle it. These must be scaled copies. When we look at B, it's asking, what about a rectangle that's 10 centimeters by 2 centimeters? So here we have a rectangle 10 by 2, and we're asking, is that equal to 12 by 3? Is it a scaled copy? So we're thinking, can we get from 10 to 12 and do the same thing to get from 2 to 3? Well, I don't see any relationship to get from 10 to 12 that's also going to work from 2 to 3. These are not equivalent fractions, therefore this cannot be a scaled copy, as in A. Question C asks us, what about 13 centimeters by 4 centimeters? So we're looking at 13 over 4, and we're asking ourselves, is that equivalent to 12 thirds? If we're using biggest side compared to smallest side, we got to use biggest to smallest. And you probably can see that there's no relationship in multiplication or division to get us from 13 to 12. That'll also work getting us from 4 to 3. Therefore, these are not equivalent fractions, and this cannot be a it cannot be a scaled copy. We have to find equivalent fractions. When we look at question D, it asked about a rectangle that is 8 centimeters by 4.5 centimeters. So if we look at 18 over 4.5 and we compare that to 12 over 3, this may be a little more difficult to see, but 18 to 12 and 4.5 to 3 definitely does have a relationship. To get from 12 to 18.5, it's 1.5 times. To get from 3 to 4.5, it's 1.5 times. So going in this direction, we can see that the new rectangle is going to be 1.5 times larger than the original. Therefore, D is a scaled copy. It's 1.5 times as big. For the final one, it asks us about a rectangle that is 80 centimeters by 20 centimeters. So if we're setting up 80 over 20, and then we also set up 12 over 3, the biggest side compared to the smallest side, as a fraction, if we simplify this first, we may be able to, it may be easier to see the relationship. So 80 and 20 are both divisible by 20. So if we simplify this, we can simplify this to 4 first. 20 goes into 84 times, 20 goes into 21 times, and now we can easily see the relationship that 4 times 3 equals 12, 1 times 3 equals 3. Therefore, these must be scaled copies because they make equivalent fractions. So we can see that the new rectangle is going to be 1/3 the size as the original, or the original is 3 times larger than this new side. Okay. Moving on, looking at question 2, it asks us about rectangle A, which has a length of 12 and a width of 8, and rectangle B has a length of 15 and a width of 10, and rectangle C has a length of 30 and a width of 15. So I went and drew what these rectangles would look like. Rectangle A, 12 by 8, rectangle B, 15 by 10, and rectangle C, 30 by 15. Note that I always put the largest number on the top and the smaller number on the side. It doesn't matter if that's reversed, just as there's consistency from A to B and B to C. So if you look at letter A in question 2, it asks, is rectangle A a scaled copy of rectangle B? Is rectangle A, which is 8 over 12, a scaled copy of rectangle B, which is 10 over 15? Now, you could have done 12 over 8 and 15 over 10, right? But if you have the smaller number on top, then for every fraction, the smaller number needs to be on top when we're looking at scaled copies, so that we have short side compared to long side, short side compared to long side, or vice versa. So now it's asking, are these scaled copies? So we're trying to find a relationship between here and here. Again, this might be hard to see. So if we simplify the fractions, 8/12 can be simplified to 2/3 because they're both divisible by 4. 8 divides by 4 2 times, 12 divides by 4 3 times. Let's see what happens when we simplify 10/15. Well, they're both divisible by 5. 5 goes into 10 2 times, 5 goes into 15 3 times. So we see that 2/3 equals 2/3. Therefore, yes, this must be a scaled copy of rectangle B. So we can answer yes, they are a scaled copy. And then what's the scale factor? Well, it's the fraction we see right here, 2/3. One of them is 2/3 the size of the other. So let's look at question B. It says, is rectangle B a scaled copy of rectangle A? And if so, what's the scale factor? Is rectangle B, which is 10/15, a scaled copy of rectangle A? Well, if A is to B, then B must be to A. We have the exact same two fractions here. These are both going to simplify to 2/3. So, yes. these are definitely scaled copies of one another. What's the scale factor? 2/3. Actually, for that one, it's going to be 3/2. If we're looking at it in the other direction, if this one is 2/3 the size of this one, then this one has to be 3/2 the size of this one. So this one's getting, from A to B, we're getting bigger. From B to A, we're getting smaller, which means it looks like those two should be switched. This A to B is getting bigger, that's 3/2, and B to A is getting smaller, that would be 2/3. All right, moving on to C. It asks to explain how you know that rectangle C is not a scaled copy of rectangle B. Rectangle C, I put as 15/30, small side to large side, compared to B, small side to large side, which is 10/15. If we simplify this fraction, 15/30, we see that that's 1/2, right? They're both divisible by 15. 15 goes into 15 once, and 15 goes into 30 twice. And if I simplify 10/15, we already said that's 2/3. Since those are not equivalent fractions, no, they cannot be scaled copies of each other, because 1/2 does not equal 2/3. Question D asks, is rectangle A a scaled copy of rectangle C? Is rectangle A a scaled copy of rectangle C? A is 8/12, B is 15/30. We already said 8/12 is 2/3 simplified, 15/30 is 1/2. Therefore, these cannot be scaled copies because they are not equivalent fractions. So, the answer is no, because 2/3 does not equal 1/2. Question 3 asks, which of these sets of angle measures could be 3 angles in a triangle? Remembering that the sum of the measures of the angles of a triangle will always equal 180 degrees. That's the triangle sum theorem. We just need to add and figure out which of these equals 180. So 40 plus 50 is 90, and 90 plus 60 is 150. 150 is not 180. A cannot be correct. Let's look at B. 50 plus 60 is 110, and 110 plus 70 equals 180. We need 180 degrees in order to form a triangle. Okay, let's take a look at the next question, which goes back to Unit 1, and it asks, in the picture, it tells us that in the picture, lines AB and lines CD are parallel. It asks us to find the measures of the following angles and to explain our reasoning. So if we look, and let's just fill in everything we know, the most obvious that you probably see is vertical angles. 38 here, then this must also be 38 degrees. Hopefully you see that this figure is congruent to this figure. So if these two angles are 38, then their corresponding angles must be 38. And then we see straight lines. And whenever we see a straight line, we know that it has to equal 180 degrees, which means the measure of this angle must be equal, or plus the measure of this angle must be 180. And 180 minus 38 is 142. So we know this angle must be 142. Its vertical angle here then must be 142, and its corresponding angle here must be 142, and obviously its vertical angle here is 142. So if we're looking at the measure of angle BCD, B to C to D, we're talking about this angle, which is 38 degrees. If we're looking at ECF, here's E to C to F. We're looking at this angle here, which is 38 degrees. And the measure of angle DCF, D to C to F, is this angle here, which is 142 degrees. All right, little preview with using the distributive property to rewrite each expression. Distributive property means we need to distribute this number out in front of the parentheses to every term inside the parentheses. So, if we look at -4, we need to multiply that by the first term, which is 2x's. Well, -4 times 2 is -8, and they are x's. And now I'm going to look at the second term, -4 times -5, which is +20. So we just distributed the -4 by multiplying it by 2x's, and then by multiplying it by -5, remembering that the sign always goes with the term. Let's take a look at number 7. We're taking 3 and we need to distribute it to all 3 terms inside. Inside we have a -4x, we have a +3y, and we have a -10. When we take 3 times -4x's, we get -12x. 3 times 3y's is 9y's. And when we take 3 times -10, we get -30. That's as far as it goes because x's stay with x's, y stays with y, and numbers stay with numbers. So there's nothing else to combine. Now, we're not going to worry about this half, right? Because we know how to take half of a number, and multiplication is of. So we need half of the 2 terms inside, the -10x and the +14. Half of -10x's is -5x's, and half of 14 is +7. So we end up with our simplification through distributing 1/2 of -10x plus 14 is -5x plus 7. Now, let's put that into practice in these 3 equations on the bottom. Because they're equations, I'm going to draw the line so that it reminds me that whatever I do on one side, I must do to the other. Now, we see that we need to distribute here. We have a -5 that needs to be distributed to x and to -3. Well, -5 times x is -5x, and -5 times -3 is +15. On the other side, we just need to bring the equals 20 down. Now, we're trying to get x alone. We always add or subtract before we multiply or divide. So we're going to undo our +15 with -15. What we do to one side, we'll do to the other. That leaves us with -5x's equal to 5. And when we now divide by -5 in order to get x alone, we will get x equal to -1. Continuing on, we're looking at 1/2 times the sum of 4x and 8, and it tells us that that's equal to -12. And since we're solving for x, we'll start by distributing. We're looking at 1/2 of 4x. We need to distribute to everything inside. We have a 4x and a +8. Half of 4x's is 2x's, and half of 8 is 4. Drop everything else exactly as it appears. Trying to get x alone, we always add or subtract before we multiply or divide. So let's subtract 4 from each side. 2x is equal to -16. -12 subtract 4 is -16, or -12 and -4 is still -16. When we divide by 2 to get x alone, we'll see that x equals -8. One more, where we're looking at 1/3 of 9x minus 12, the difference of 9x minus 12, and we see that that set is equal to 8, so we're asked to solve for x. We need to apply the distributive property, taking 1/3 of 9x as 3x, and 1/3 of -12 is -4. Drop everything else exactly as it appears. We'll undo -4 with +4. What we do to one side, we do to the other. We get 3x equal to 12. And when we divide by 3 to undo this multiplication with division, we get x equal to 4. You'll continue working on the next page in your packet.